Welcome to a special episode of Software Engineering Daily. This is our first piece of premium content. With premium content, our goal is to look deeper into topics that we cover in normal episodes of Monday through Friday Software Engineering Daily. With this episode, it's being released on Saturday, and we're exploring Kubernetes in an editorial context. We're talking about its implications and what may have fallen through the cracks in our day-to-day interviews with professionals who are working deeply in the Kubernetes space. This episode is available for free, but future premium episodes will only be available as podcast episodes to premium subscribers. We plan to release premium content roughly once a month, and subscribers to Software Engineering Daily also have access to every episode without ads. So if you become a paid subscriber, which you can do by going to softwaredaily.com and clicking on subscribe, you will not hear ads in your episodes if you listen on the Software Engineering Daily app or on our website, softwaredaily.com. We went through the entire back catalog and stripped out the ads so that subscribers could choose to opt out of that experience. If they are paying us with money, then we are not going to charge them by putting advertisements in their ears, although we love our advertisers. If you want to subscribe, again, you can go to softwaredaily.com and click subscribe in the upper right. Software Daily is our new website that we've built from scratch in open source, and we have some cool features that we're working on, including community features and supplementary links for episodes. If you become a paid subscriber, you are helping us grow the business, you're building out our platform, and you're helping us provide more content. If you have any questions or feedback on this new aspect of Software Engineering Daily, the subscriber paid model, please email me, jeff@softwareengineeringdaily.com. And with that, let's get on with this special premium episode, the Gravity of Kubernetes. Kubernetes has become the standard way of deploying new distributed applications. Most new internet businesses started in the foreseeable future will leverage Kubernetes, whether they realize it or not. Many old applications are migrating to Kubernetes too. Before Kubernetes, there was no standardization around a specific distributed systems platform. Just like Linux became the standard server-side operating system for a single node, Kubernetes has become the standard way to orchestrate all the nodes in your application. With Kubernetes, distributed systems tools can have network effects. Every time someone builds a new tool for Kubernetes, it makes the other tools better, and it further cements Kubernetes as the new standard. Google, Microsoft, Amazon, and IBM each have a Kubernetes as a service offering, making it easier to switch infrastructure between the major cloud providers. We're likely to see DigitalOcean, Heroku, and longer tail cloud providers offer a managed hosted Kubernetes eventually. In this editorial, I explore the following questions. Why is this happening? What are the implications for developers? How are cloud providers affected? And what are the new business models that are possible in a Kubernetes standardized world? Software standards. Standardized software platforms are both good and bad. Standards allow developers to have expectations around how their software will run. If a developer builds something for a standardized platform, they can make smart estimations about the total addressable market for that piece of software. If you write a program in JavaScript, you know that it will run in everybody's browser. If you create a game for iOS, you know that everyone with an iPhone will be able to download it. If you build a tool for profiling garbage collection in .NET, you know that there is a large community of Windows developers with memory issues who can buy your software. Standardized proprietary platforms can lead to massive profit returns for the platform provider. In 1995, Windows was such a good platform that Microsoft could sell a CD in a cardboard box for $100. In 2018, the iPhone is so good that Apple can take 30% from all app sales on its platform. Proprietary standards lead to fragmentation. Your iPhone app does not run on my Kindle Fire. I can't use your Snapchat augmented reality sticker on Facebook Messenger. My favorite digital audio workstation, which is called FL Studio, only runs on Windows. So I have to keep a Windows computer around in order to make music. When developers see this fragmentation, they groan. They imagine the greedy capitalists who are making money at the expense of software quality. Developers think, why can't we all just get along? Why can't we have things be open and free? Developers think, we don't need proprietary standards. We can have open standards. And this happened with Linux. These days, new server-side applications are mostly in Linux. There was a time when that was controversial, and I have a picture in the article that accompanies this narration where you see in early 1997 the market for Apache web server just takes off, and Apache is part of the LAMP stack, Linux, Apache, MySQL, PHP, which became the predominant server stack as opposed to Microsoft, which dropped in market share in the late 90s, early 2000s. And more recently, we saw a newer open standard with Docker. Docker gave us an open, standardized way of packaging and deploying and distributing a single node. And this was hugely valuable. But for all the problems that Docker solved, it highlighted a new problem. How should we be orchestrating all of these nodes together? After all, your application is not just a single node. You know that you want to be deploying a Docker container, but how are your containers communicating with each other? How are you scaling up instances of these containers? How are you routing traffic between container instances? Container orchestration. After Docker became popular, a scramble of open source projects and proprietary platforms emerged to solve the problem of container orchestration. Mesos, Docker Swarm, and Kubernetes each offered a different set of abstractions for managing containers. Amazon ECS offered a proprietary managed service that took care of installation and scaling of Docker containers for AWS users. Some developers did not adopt any orchestration platform. These developers used Bash and Puppet and Chef and other tools to script their deployments. Whether a developer was deploying their container by using an orchestration platform or a script, Docker sped up development, and it made things more harmonious between developers and operations. As more developers deployed containers with Docker, the importance of the orchestration platform was becoming clear. A container is as fundamental to a distributed system as an object is to an object-oriented program. Everyone wanted to be using a container platform, but there was a struggle between these different platforms, between Docker Swarm and Mesos and Kubernetes, and it was hard to see which would come out on top, or if it would be a decades-long struggle like iOS versus Android. This struggle between the different container orchestration platforms was causing fragmentation. And that's not because any of the popular orchestration frameworks were proprietary. This wasn't like the early 90s or like today with mobile platforms where you have fragmentation because you have certain proprietary systems. This was because each container orchestration community, Swarm and Kubernetes and Mesos, they had all invested so much in their own ecosystem. So from 2013 to 2016, there was this anxiety among Docker power users because if you choose a container orchestration framework, you're making a huge bet. If you chose the wrong orchestration system, it would be like opening a movie store and choosing HD DVD over Blu-ray. if you mess up, then you choose the wrong container orchestration system, and once people centralize on one of them, then you're in the wrong system. And the whole thing is that around this time, I was reporting on it, and the war between container orchestrators felt like it was going to be a winner-take-all affair. This did not feel sustainable, where people were arguing over which container orchestration system you should use, and there's differences, and you don't want to use two different container orchestration systems. It just felt like a winner-take-all affair. And as in any war, there was a fog that was hard to see through. I was reporting on this, and I was recording podcast after podcast with container orchestration experts where I would ask them some form of the question, so which container orchestration system is going to win? Who's going to win? Which one is the best? Is it Docker? Is it Docker Swarm? Is it Kubernetes? Is it Mesos? Which one's the best? And I did this until somebody that I respected a lot told me that I was asking the wrong question. I shouldn't be asking who is going to win the container orchestration wars, because it's just picking sides. It's really a less interesting question than evaluating the technical trade-offs between the orchestrators. And that's partly because these orchestration systems are schedulers. They're scheduling systems, and we're going to have schedulers for a really long time. And so looking back, I regret buying into the narrative of this war between the container orchestrators, because as these debates were raging on, the smartest people in the room were mostly having calm, scientific discussions, even when reporters like me were getting worked up and thinking that this was a story about tribalism and who's the best. The conflicts between the different container orchestrators were not so much about tribalism as they were about differences of opinion and developer ergonomics. How should you build a container orchestrator? There were genuine differences of opinion around this. But okay, maybe this war wasn't only about differences of opinion. There was a boatload of money to be made in this space. We're talking about contracts with billion-dollar legacy organizations, banks and telcos and insurance companies. And around this time, they're all making their way onto the cloud. So the container orchestration system is this place where you're battling for mind share for these huge contracts with legacy organizations. And that's part of why there was so much acrimony around who was going to be the container orchestration system to rule them all, because there was so much money to be made by betting on the right container orchestration system. So if you're in the business of helping a telco move on to the winning platform, business is going to be really good. But if you end up championing the wrong platform, it's like you end up with a warehouse full of HD DVDs. Nobody wants to move on to the container orchestration platform that didn't win. The time where the conflict was the worst was when I was reporting on this near the end of 2016. There were these rumors about Docker potentially forking so that Docker, the company, could change the Docker standard to fit better with their container orchestration system, Docker Swarm. And this was kind of plausible because people were unsure, how is Docker, the company, going to make money? You know, they have a high valuation, and that they built this standard for deploying containers, which is incredible. But people were wondering, okay, how are they going to build this into a really big business? And I think some people were speculating that it was going to be based off of their container orchestration system, Docker Swarm. And so people were thinking, oh, are they going to manipulate the standard to change it so that this standard favors Docker Swarm, so that Docker itself favors a specific container orchestration system? At least that was how I understood the arguments of people who are criticizing Docker around this time. I would love to be corrected if I have the history wrong on this. But the thing is, even in those times when people were arguing about how should we orchestrate our containers, it made sense to be optimistic because this was incredible. We were moving towards a time where people could deploy their own distributed systems easily. And you could tell that we were moving towards something that was going to be really impactful, really important in the software engineering world. And this was creative destruction. Creative destruction is painful, but it's a sign of progress. And in the struggle for container orchestration dominance, there was a lot of creative destruction. When the dust cleared around the end of 2016, Kubernetes was the clear winner. And I have this depicted pictorially in the article accompanying this, where you see a graph of Google Trends where you see Kubernetes just taking off relative to Mesos and Docker Swarm as a container orchestration system. It's just become so popular. And with Kubernetes becoming the safe choice, the CIO at this telco or the insurance company or whatever other giant legacy enterprise you want to talk about, they now feel comfortable adopting container orchestration at their enterprise. So when you get telcos and the banks and all these giant organizations that want to move in a specific direction, it's like a feeding frenzy for vendors. So you get these monitoring and logging and all these other types of vendors who now have a specific customer segment that they can sell to. And so as the vendors are feeling more comfortable investing in Kubernetes-specific tooling to sell to these CIOs, then you get a really magical situation happening, because these vendors get a bunch of venture capital, and all this money is not necessarily being wasted over zero-sum conflicts where we're building different systems for different container orchestration systems. It's just everybody is building for Kubernetes now. So to articulate it, the open source developers are all rowing in the same direction. Everybody is excited about what to build. We're all building for Kubernetes, and it's great. We know this stuff is going to compound. You have major enterprises, both new and legacy enterprises, that are buying into Kubernetes. You have major cloud providers that are ready with low-cost Kubernetes as a service. And then you have numerous vendors of logging and monitoring and security and compliance software, and they're all thrilled because the underlying software stack that they have to integrate with is becoming really predictable. And so you've got venture capitalists that are pouring money into that. So that creates this great situation for software engineers, and that's really what the rest of this article is about. Going multi-cloud. Today, the most lucrative provider of proprietary backend developer infrastructure is Amazon Web Services. Developers do not view AWS resentfully because AWS is innovative and empowering and cheap. If you're paying AWS a lot of money, that probably means that your business is doing well. With AWS, developers do not feel the level of lock-in that was administered by the dominant proprietary platforms of the 90s. But there is some lock-in. Once you're deeply embedded in the AWS ecosystem, you're using services like DynamoDB or Amazon ECS or Amazon Kinesis, it can become a daunting task to move away from Amazon. With Kubernetes creating an open, common layer for infrastructure, it becomes theoretically possible to lift and shift your Kubernetes cluster from one cloud provider to another. If you decided to lift and shift your application, you would have to rewrite parts of that application to stop using the Amazon-specific services, such as Amazon S3. For example, if you wanted an S3 replacement that would run on any cloud, you could configure a Kubernetes cluster with Rook, and you could start storing objects on Rook with the same APIs that you would use to store them on S3. We have done a show about Rook, which may or may not have aired by the time this episode airs, but it's a cloud-agnostic way of building an object storage or a file storage system on top of Kubernetes. And we'll get into more distributed systems that you can build on top of Kubernetes a little bit later on in this episode. But The point I'm trying to make here is that there are these services that people are building on top of Kubernetes that allow you to do things that might previously just have been easy to do within a specific cloud. So like in the past, you could have moved Amazon S3 workloads to a Google object storage system, but there may not have been a system that was as open that you could have ported from one cloud provider to another. And this is a nice option to have, the ability to move between cloud providers with certain infrastructure systems, such as Rook. But I actually haven't heard of anyone lifting and shifting their core application away from a cloud. Really, the only major migration that I have heard of is the Dropbox migration, in which Dropbox was basically a layer of usability on top of Amazon S3 when they started, and then they eventually moved off of Amazon for their core storage system and moved it into a data center that they're controlling, and that was an epic migration. It took 2.5 years. We did an episode about it. There's a great Wired article about it that I linked to in this episode. And certainly there's someone out there other than Dropbox who spends so much money on Amazon S3, and maybe they're disappointed with the level of lock-in, or they don't like the fact that they're locked in. They're considering spinning up their own object store. But if they actually did want to migrate fully away from Amazon, it would be a huge effort to do such a migration. And a lot of businesses that are doing well, it just economically, it does not make sense to do that kind of migration. So Kubernetes could be used for widespread lifting and shifting, but I'm not sure if we'll see that anytime soon. I would love if people told me I was wrong, and there are reasons for that this will happen. In any case, I think a more likely scenario is that Kubernetes will actually become a ubiquitous control plane that a given enterprise will use on multiple clouds. Let me explain what I mean by that. I want to do it by analogy first. So Node.js is a useful analogy. Why do people like Node.js for their server-side applications? It's not necessarily because Node.js is the fastest web server. It's because people like to use the same language on both the client and the server. Just like Node.js lets you move between your client and your server code without having to switch languages, that painful context switch, Kubernetes will let you switch between clouds without having to change how you think about operations. On each cloud, you're going to have some custom application code that's running on Kubernetes that interacts with the managed services provided by that cloud. Companies want to be multi-cloud, and that's partly for disaster recovery, but there's actual upside rather than just downside protection to having access to managed services on the different clouds. If you look at the managed services on the different clouds that are available, they are getting different and exotic, and it's not commodity anymore. One emerging pattern that I've seen to split infrastructure between different clouds for different purposes is between AWS for user traffic and Google Cloud for data engineering. One company that uses this pattern is Thumbtack. We did a show, 2 shows actually, about Thumbtack and their infrastructure. And here's a quote from that show. At Thumbtack, the production infrastructure on AWS serves user requests. The log of transactions that occur gets pushed from AWS to Google Cloud, and the data engineering occurs on Google Cloud. The transaction records on Google Cloud are queued in Cloud PubSub, a message queuing service. So transactions go from AWS to Google Cloud via this PubSub service, and then the transactions are pulled off of the queue and stored in BigQuery, which is a system for storage and querying of high volumes of data. That's a Google system. BigQuery is used as the data lake to pull from when orchestrating these machine learning jobs. And machine learning jobs are run in Cloud Dataproc, which is a Google managed service that runs Apache Spark. After training a model in Google Cloud, the model is deployed on the AWS side, where it serves user traffic. On the Google Cloud side, the orchestration of these different managed services is done by Apache Airflow, an open source tool that is one of the few pieces of infrastructure that Thumbtack does have to manage themselves on Google Cloud. That's the end of the quote. So here we see a model where Google Cloud provides Thumbtack with data engineering, and Amazon Web Services provides Thumbtack with the user requests. So Thumbtack is using AWS to serve user requests and Google Cloud for data engineering and queuing in PubSub. And Thumbtack trains its machine learning models in Google and deploys them to AWS. And this is just the way things are today. Thumbtack might eventually use Google Cloud for user-facing services as well. Maybe they'll eventually use AWS for data engineering services. I think the ideal world is that we wouldn't really have to think about what is on what cloud. We would just have this buffet of options to choose from. And I'm not sure if Thumbtack uses Kubernetes to run Apache Airflow, but the usage of Apache Airflow on the Google Cloud side illustrates that there are still tools that are not available as managed services that are the top of the line, I suppose. I assume Thumbtack knew what was at the top of the line, and they chose to go with an open source tool they chose to go with Apache Airflow, this open source tool, instead of choosing a Google managed service for the purpose that Apache Airflow is solving. So here we see an example where on both sides of the cloud, on both clouds, on Google Cloud and on AWS, they use ECS, I believe, to run their Node.js applications, or maybe it's a Java application, but basically the applications that serve user requests are running on AWS in containers, and then on Google Cloud, they do have this non-managed service, Apache Airflow, that they're running. And so this illustrates that you are going to want to have some of your own infrastructure on every cloud. And what I'm suggesting is that Kubernetes could be the layer where you're managing this bespoke infrastructure that you're building in a given system, on a given cloud. And I've also got a picture in the article that accompanies this episode from a Japanese company's architecture. And most of the text is in Japanese, so I can't read it, but it shows a similar setup where they have Amazon EC2 managing the user requests, and then they have Google Cloud Storage and Google BigQuery managing the data engineering. So this seems like a pattern to me. You might have a GKE Kubernetes cluster on Google to orchestrate the workloads between BigQuery and Cloud PubSub and Google Cloud ML, and you've got an Amazon EKS cluster to orchestrate DynamoDB, Amazon Aurora, and maybe your production Node.js application. My main point here is that cloud providers are not replaceable commodities. The services provided by the different clouds will get increasingly exotic and differentiated. Enterprises will benefit from having access to the different services on the different cloud providers. It remains to be seen what will be the standard patterns for having access to these different managed services, as well as having access to your own code that you want to write. But we'll get into some other discussions of that a little bit later on the show. Maybe companies don't want Kubernetes. Maybe they want to be serverless, but I think Kubernetes is going to be here to stay for a while. Distributed systems distribution. Services like Google BigQuery and AWS Redshift are popular because they give you a powerful, scalable, multi-node tool with a simple API. Developers often choose these managed services because they are so easy to use. But you don't see these types of paid tools for single-node applications as often these days. I don't pay for Node.js, I don't pay for React.js, I don't pay for Ruby on Rails. Tools for a single node are much easier to operate than tools for a distributed system. It's harder to deploy Hadoop across several servers than it is to run a Ruby on Rails application on my laptop. With Kubernetes, this is going to change. If you're using Kubernetes, you can use a distributed systems package manager called Helm. This is like NPM for Kubernetes applications. If you're using Kubernetes, you can use Helm to easily install a complicated multi-node application, no matter what cloud provider you're on. Here's a description of Helm. Helm helps you manage Kubernetes applications. Helm Charts helps you define, install, and upgrade even the most complex Kubernetes application. Helm Charts are easy to create, version, share, and publish. So start using Helm and stop the copy and paste madness. This is a package manager for distributed systems. Amazing. I'm looking at what you can install right now, and it's things like Hadoop, IPFS, Istio, WordPress, Jenkins, Kafka. Distributed systems are hard to set up. Ask anybody who has set up their own Kafka cluster. And I think Helm is going to make installing Kafka as easy as installing a new version of Photoshop on your MacBook. And you'll be able to do this on any cloud. Before Helm, as far as I know, the closest thing to a distributed systems package manager that had the potential to reach a large audience was the marketplace that you find on AWS or Azure or the Google Cloud Launcher. And here again, we see how proprietary software platforms can lead to fragmentation. It's not a unified marketplace across the different cloud providers. Before Helm, there was no standard platform-agnostic way of one-click installing Kafka or Hadoop. You can find a way to one-click install Kafka on AWS, Google, or Azure, but each of these installations had to be written independently for that specific cloud provider. And to install Kafka on DigitalOcean, you need to follow a 10-step tutorial. Helm represents a cross-platform system for distributing multi-node software on any Kubernetes instance. So you could use an application installed with Helm on any cloud provider or on your own hardware. You could easily install Apache Spark or Cassandra, and these are systems that are notoriously difficult to set up and operate. This to me seems like a huge deal. Helm is a package manager for Kubernetes, but it also looks like the beginnings of an app store for Kubernetes. With an app store, you could sell software for Kubernetes. Maybe instead of app store, I should say distribution mechanism. But if you think about it, what is the distribution mechanism for distributed systems today? It's basically software as a service. And it's just whatever software as a service you buy. So this might be a way of a distribution mechanism for distributed systems where you can purchase it or use it at the open source or the platform level in a way that's a lot easier than the status quo today. What kind of software could you potentially build or sell with this distributed systems package manager? Well, you could sell enterprise distributions of distributed systems platforms like Cloudera Hadoop or Databricks Spark or Confluent's Kafka distribution. You could make it easy to install monitoring systems like Prometheus, multi-node databases like Cassandra, these systems that are really hard to install. They're notoriously hard to install. That's, I think, why there are more people who install a single node system like Ruby on Rails. Ruby on Rails is very popular. I mean, Kafka is popular, but the level of popularity is not as high as Ruby on Rails. And I think that's partly because it's not easy to deploy. And maybe you could even sell higher level consumer-grade software like Zendesk. So imagine a Kubernetes version of Zendesk. Zendesk is help desk ticketing software. It has a messaging system. It has a support system. It has customer intelligence systems. And this is a product that requires multiple nodes interacting together in order to be resilient to node failures. And that's part of why it makes a great software as a service tool, because customers don't really want to worry about these kinds of distributed systems failures. The idea of a self-hosted Zendesk might sound kind of crazy, but somebody could build that, and they could sell it in the form of a proprietary binary at the cost of a flat fee instead of a subscription. If I could sell you a $99 Zendesk for Kubernetes, you could install it on your Kubernetes cluster on AWS, and you're going to end up saving a lot of money on support ticketing software because you're just paying a fixed cost for it. It's a one-time setup fee. Maybe you occasionally have a problem with it that you need to pay for support on demand, but that could be better for some customers than paying a subscription SaaS fee. Enterprises are often running their own WordPress to manage a company blog. Is the software for Zendesk that much more complicated than WordPress? I don't think so. But enterprises are much more scared of managing their own help desk software than managing their own blogging software. And it's worth thinking about why that is. Why is it scary to run your own help desk software? I run a pretty small business, but I subscribe to a lot of different software as a service tools. Some things that I subscribe to are an expensive WordPress host, an expensive CRM for advertising sales. I subscribe to MailChimp for my newsletter. And I pay for these services because they are super reliable and secure. And they're complex multi-node applications. I would not want to host my own. And by the way, I wouldn't want to host my own email server either. I use Gmail for my email. I wouldn't want to support any of this stuff. I don't want to be responsible for technical troubleshooting when my newsletter fails to send. I want to run less software, as we discussed in an episode recently with the interview of a director of engineering from Intercom. That's one of their philosophies, is run less software. But I'm not really afraid that my single node software is going to break. The software that I use from a single node tends to be much less expensive because I don't have to buy it as a service. The software that I use to write music is one of the rare pieces of software that runs on a single node, but I've paid for. Photoshop also has a one-time fixed cost. And then after you pay the one-time fixed cost for things like Photoshop or music editing or movie editing, you just pay for the electricity to run your computer. But other than that, you have no ongoing capital expense to run this kind of software. Eventually, multi-node applications are going to get as reliable as single-node applications. And we're going to see changes in the pricing models when that happens. Because if you think about it, your laptop is a distributed system. You've got different components that are communicating across a network within your laptop. And the networking between different computers, between different nodes, is harder. It's more complex. It's more vulnerable to failures. But there's going to be a time where we can treat the distributed infrastructure as being very reliable. So maybe someday I will be able to purchase a Zendesk for Kubernetes. And the Zendesk for Kubernetes will give me everything I need from a help desk. It will spin up an email server. It will give me a web front end to manage tickets. And it's going to be reliable. And if anything goes wrong, I can pay for support when I need it. And I use this as an example not because I think Zendesk is a bad service. I think it's a fantastic service. But it would be cool if there were a fixed pricing model for a Zendesk-like tool, and it was also easy to install. I know there are some open source Zendesk systems, Zendesk-like systems, help desk ticketing systems, but I think that there is a big burden to the installation process, and that's the connection between Helm and this idea of a, quote, Zendesk for Kubernetes. Is with Helm, I think you might have this system for distribution, for software distribution, that really changes the game for distributed systems. That's all speculative. I would love to hear your thoughts on it if you want to send me an email. Metaparticle. With Kubernetes, it becomes easier to deploy and manage distributed applications. With Helm, it becomes easier to distribute those applications to other users. But it's still pretty hard to develop distributed systems. This was the focus of a recent Cloud Native Con KubeCon keynote by Brendan Burns, and the keynote was called "This Job is Too Hard: Building New Tools, Patterns, and Paradigms to Democratize Distributed Systems Development." And in the article, I have a picture of a slide that Brendan had in his talk, and that slide shows an analogy between the single node operating system world and the multi-node operating system world. And the analogy is that in the single node operating system world, you have objects, and those objects are orchestrated within a runtime. And that runtime is facilitated by a set of standard libraries that make it easier to work within the operating system. It's easier to forget that the operating system standard libraries within your laptop are pretty complicated. And then on the right side of his analogy, he's got the multi-node world. And he says, containers are like objects, and Kubernetes is like that runtime. And he's talking about Metaparticle as this idea of the standard library for distributed systems. He's saying that just like we needed a set of standard libraries to make it easier to build single node applications, we need a standard library for multi-node applications. So this project is called Metaparticle, and Metaparticle is a standard library for cloud native development. The goal is to democratize distributed systems. And I've got an excerpt from Brendan's introductory article about Metaparticle. He writes, "Cloud native development is bespoke, complicated, and limited to a small number of expert developers. Metaparticle changes this by introducing a set of utilities in familiar programming languages that meet the developer where they are and enables them to begin to develop cloud-native systems using familiar language features. Metaparticle builds on top of Kubernetes primitives to make distributed synchronization easier as well. It supplies language-independent modules for locking and leader election as easy-to-use abstractions in familiar programming languages." That's the end of his quote. After decades of distributed systems research and applications, we have some patterns that have emerged about how we build these systems. We need to do things like locking a variable so that two nodes will not be able to write to that variable in a non-deterministic fashion. We need a way to do master election so that the master node dies, the other nodes in the distributed system can pick a new node to orchestrate the system. And today we use tools like etcd and Zookeeper to help us with master election and locking. And these tools have an onboarding cost. Brendan illustrates this with the example of Zookeeper. Zookeeper is used by both Hadoop and Kafka to do master election. And Zookeeper takes significant time and effort to learn how to operate. During the construction of both Hadoop and Kafka, which are, if you didn't know, very important distributed systems projects that form the core infrastructure of many of the internet companies that you know of, during the construction of Hadoop and Kafka, the founding engineers of Hadoop and Kafka, they engineered their systems to work with Zookeeper to maintain a master node. If I'm writing a system to do distributed MapReduce, I would like to avoid thinking about node failures and race conditions. That's not the core job of a distributed MapReduce system. And Brendan's idea is to push these problems down into a standard library so that the next developer who comes along with a new idea for a multi-node application has an easier time. And there's an important meta point here. Metaparticle is built with the assumption that you are on Kubernetes. This is a language-level abstraction that is built with an assumption about the underlying distributed operating system. And this brings us back to standards, the importance of standards, and the importance of everybody being on this same distributed operating system platform. We can start to make very big assumptions about the downstream users of our projects. And this is why Kubernetes is so important and so mind-blowing, because it's a layer of standards across a world of heterogeneous systems. Serverless workloads. Functions as a service, often called serverless functions, are a powerful, cheap abstraction that developers can use alongside Kubernetes or on top of Kubernetes, or in some cases instead of Kubernetes altogether. And here I'd like to review the modern landscape of serverless applications and then consider the relationship between serverless and Kubernetes. A quick review on functions as a service. Functions as a service are deployable functions that run without an addressable server. Functions as a service deploy, execute, and scale with a single call by the developer. Until you make that call to the serverless function, your function is not running anywhere, so you're not using up resources other than the database that is storing your raw code. When you call a function as a service, your cluster will take care of scheduling and running that function. You don't have to worry about spinning up a new machine and monitoring that machine and spinning the machine down once it becomes idle. You just tell the cluster that you want to run a function, and then the cluster executes it and returns the result. And functions as a service get described as being serverless, and that term is appropriate. It's also appropriate to describe these managed services that we discussed earlier, like Google BigQuery or Amazon ECS or Amazon Redshift. These are also described in the purview of serverless. But for the purposes of this section, when I say serverless, I'm only referring to functions as a service, unless I explicitly say so. But it's really important that people who are trying to understand this space understand the difference between these two types of serverless. There's the functions as a service, serverless, and then the managed services type of serverless. When you deploy a serverless function as a service, the function code is not actually deployed. Your code sits in a database in plain text. And when you call the function, your code is being taken out of the database entry, loaded onto a Docker container, and executed. And then it's spun down when that container is not being used anymore. This is why the function as a service model is so cheap. AWS Lambda pioneered this idea of a function as a service in 2014. And since then, developers have been thinking of all kinds of use cases. There's a comprehensive list of how developers are using serverless that I have linked to in the show notes that goes with this episode. There's this shared Google Doc that was created by the CNCF, that's the Cloud Native Computing Foundation, Serverless Working Group. It's a 34-page document at the time of this episode creation, and it's got tons of information about how people are using these functions as a service. These things are here to stay, and they're going to be really impactful on how people build systems in the near future. But for how people are using them in production today, I have seen at least two clear applications that you can delineate. There's obviously more, but broadly speaking, the two clear applications that I've seen are you've got compute that can scale up quickly and cheaply in response to bursty workloads. For example, we did a show about Yubble, where this was a social media company that had a problem with extremely bursty workloads, where when these particular users who were extremely popular would log on to the website, tons of other people would log on. And then for the rest of the day, they would not have that much traffic. So there's these extreme spikes in workload, and functions as a service are really useful for scaling up quickly and cost effectively in response to those bursty workloads. The other type of workload that I have seen commonly is the event-driven glue code, where if you have a variable workload frequency, for example, you have an event sourcing model with a variety of database consumers that are pulling off of an event queue, you've got wide variety in the workload frequency. So this is kind of like my first example with the bursty workloads. In any case, it's worth understanding how these things work at a fundamental level because there are lots of applications for them, and I could broadly describe them as glue code or bursty workload responses, but it's more important to understand what they're doing fundamentally. And for each of these different cloud providers, they have a function as a service platform. So to create a function as a service platform, a cloud provider provisions a cluster of Docker containers called invokers, and these invokers wait to get blobs of code scheduled onto them. When you make a request for your code to be called to execute, there's this period of time that you have to wait for that code to be loaded onto an invoker and executed. And this time spent waiting is the cold start problem. And that's cold start problem exists because your code is not actually running in a container when you call it. It's sitting as raw text in a database, and the code has to be taken out of the database, scheduled onto a container, and then the container has to be fully spun up. That's the cold start problem. And the cold start problem is one of the trade-offs that you make if you decide to run part of your application on functions as a service. You don't pay for the uptime of a server that isn't going to do any work, but when you want to call your function, you have to wait for that code to be scheduled onto an invoker. That's the trade-off. It's a really interesting set of trade-offs that are worth exploring. On AWS, there are invokers that are designated for whatever requests for AWS Lambda come in. On Microsoft Azure, there are invokers designated for Azure function requests. On Google Cloud, there are invokers that are reserved for Google Cloud functions. So on each of these cloud platforms, they've got a huge provisioning of containers that are just waiting to have functions scheduled onto them. For most developers, using the function as a service platforms from AWS or Microsoft or Google or IBM are going to be fine. When you want a function as a service, you're just going to say, okay, I'm going to take it off the shelf from a cloud provider. The costs are low. The cold start problem is not that problematic for most applications. There's some ways around it. And most developers are going to be fine with that. But some developers will want to get their costs even lower, or they might want to write their own scheduler that defines how code gets scheduled onto invoker containers. And these developers can roll their own serverless platform rather than using the serverless platform of a cloud provider. And there's some open source technologies that help with this. There's open source function as a service projects such as Kubeless. There's also IBM OpenWhisk. There's Fission. And the important thing to know about these function as a service platforms is that you can provision your own serverless cluster on top of Kubernetes. You can define your own pool of invokers, and you can determine how containers are scheduled against different jobs. You can decide on how to solve the cold start problem for your own cluster. And once you spin up a container, you can determine how long you want to wait until that container gets spun down. And the open source function as a service for Kubernetes is just one type of resource scheduler. There are a bunch of other resource schedulers that we're going to see on top of Kubernetes. Developers are always building new schedulers in order to build more efficient services on top of those schedulers. And I think that's the important thing to take away from this discussion of Kubernetes versus serverless architecture. Because you could say, hey, I could deploy my application to Kubernetes, but I could also just deploy it to serverless functions and have it magically scale. And that's true. But the important thing to remember is that there's a gradient between those different types of deployments, where you've got a deployment that's always up and a deployment that only spins up when you make a call to the function as a service platform, you've got a set of trade-offs along that gradient between them. And that's what we're going to see people explore with custom schedulers built on top of Kubernetes. So what other types of schedulers could you build? What other types of schedulers could you build on top of Kubernetes? Well, here it's worth thinking about what are the types of distributed systems that we would want to make it easy to deploy to Kubernetes. We're going to need different application primitives in order to build bigger and more exotic distributed systems. One example of an exotic distributed system that comes to mind is this thing that Amazon announced at AWS reInvent this year called Amazon Aurora Serverless. It's a serverless database which scales storage and compute up and down automatically. There was a good blog post from Jeff Barr that explained what AWS Serverless Aurora does. And it says, when you create an Aurora database instance, you choose the desired instance size and have the option to increase read throughput using read replicas. If your processing needs or your query rate changes, you have the option to modify the instance size or to alter the number of read replicas as needed. This model works really well in an environment where the workload is predictable, with bounds on the request rate and processing requirement. Here Jeff is talking about the classic Aurora database. This is an Amazon database that you have access to, but it requires some manual configuration in order to respond to bursty workloads. So we can see where this is going. He's talking about this new Amazon serverless Aurora database that performs well under bursty workload conditions. So Jeff continues, in some cases, the workloads can be intermittent and or unpredictable, with bursts of requests that might span just a few minutes or hours per day or per week. Flash sales, infrequent or one-time events, online gaming, reporting workloads, hourly or daily, dev and test environments, brand new applications, all of these things fit the bill. Arranging to have just the right of capacity can be a lot of work. Paying for it on steady-state basis might not be sensible. Because storage and processing are separate, you can scale all the way down to zero and pay only for storage. I think this is really cool, and I expect it to lead to the creation of new kinds of instant-on, transient applications. Scaling happens in seconds, building upon a pool of warm resources that are raring to go and eager to serve your requests. That's the end of Jeff Barr's blog post, which I link to in the show notes for this episode. And the point I'm trying to make here is that if you wanted to build that serverless database in the open today, if you wanted to build it on your own, what would you do? How would you build that? We're not surprised that AWS can build something like this, but it's hard to imagine how it could emerge as an open source project until you look at Kubernetes. This is the type of system that random developers could build on top of Kubernetes. If you wanted to build your own serverless database on top of Kubernetes, you've got a number of scheduling problems to solve. You need different resource tiers for networking and storage and logging and buffering and caching. For each of those resource tiers, you need to define how resources will get scheduled to scale up and down in response to demand. And so the point here is that we'll see custom schedulers for these kinds of things. Just like Kubeless offers a scheduler for the small bits of functional code that we see in the function as a service space, we might see other custom schedulers that people use as building blocks for bigger applications. And I say this because scheduling has been around forever. It is an unsolvable problem. It's a super complicated problem. I did a show with Adrian Cockcroft. It was one of my favorite shows about schedulers and all the different types of scheduling that he has seen in his career. And I think this is a problem that will be explored in depth on Kubernetes. And then once you actually build your serverless database, by the way, perhaps you could sell it on the Helm App Store as a $99 one-time purchase. just like I described earlier with that Zendesk idea. Conclusion. I hope you have enjoyed this tour through some Kubernetes history and some speculation about the future. As 2018 begins, here are some areas that we'd like to explore this year. How do people manage deployment of machine learning models on Kubernetes? We did a show with Matt Zeiler where he discussed deploying machine learning through Kubernetes, and it sounded complicated. Another question, is Kubernetes useful for self-driving cars? If so, how do you deploy a cluster on a car? And do you only need one cluster for the car, or do you have multiple clusters running within a single car? What does a Kubernetes IoT deployment look like? If you've got Kubernetes running at a oil refinery, where do you put different deployments? Do you have multiple deployments? Does it make sense to run Kubernetes across a set of devices that have intermittent network connections across an oil refinery? What are the new infrastructure products and developer tools that will be built with Kubernetes? What are the new business opportunities? I know I discussed the Zendesk idea, the idea of building a serverless database on top of Kubernetes. I could see both of those being potential business opportunities. I'm not sure if there would be giant business opportunities, but they are interesting business opportunities. What are the other new business opportunities now that we are moving towards a world where we have a standardized, distributed operating system? What can we build? Kubernetes is a fantastic tool for building modern application backends, but it's still just a tool. If Kubernetes fulfills its mission, it will eventually fade into the background. There will come a time when we talk about Kubernetes like we talk about compilers or operating system kernels. Kubernetes will be lower-level plumbing that is not in the purview of the average application developer. But until then, we'll continue to report on it. Thanks for listening to Software Engineering Daily.